today's class. For today, we'll be treating friction. By definition, friction is simply a force that acts at the surface of separation between two bodies and tends to oppose the motion of one body over the other. That's your definition for friction. Alternatively, we can define friction as a force that opposes the relative motion of a body over the other. Now, from the definition there is something you should pick out from there. Number one is that friction is a force that opposes motion. And number two, it opposes the motion of one body in contact with another body. That means for friction to occur, a body must be moving relatively to another body. So that's your definition for friction. Next up, let's look at where exactly does friction act. Now, we said friction is a force, and from what we know from an idea of vectors and scalar, we said force is a vector quantity, and force being a vector quantity means it must have magnitude and then direction. So the question is this: what is the direction of frictional force? Now, we said frictional force tends to oppose the motion of a body, and hence, if it opposes the motion of a body, or for a force, perhaps friction, to oppose the motion of a body, it must be acting in the opposite direction of that body. Let's say, for instance, I have a surface like this. Let's use two scenarios. Let's say scene A or scene 1. For scene 1, let's have a body on a surface. Let's use a rough surface, because if it's a smooth surface, friction does not really occur in smooth surfaces. So we'll do this, showing that it's a rough surface. Let's have a here. Alright, now when a body is resting on a rough surface, two forces act on this body. The first one there is the weight of the body. Of course, the weight of the body acts downward. So you have weight acting downward. For a body resting on a rough surface, the weight acts downward. Next up, from Newton's third law of motion, it says to every action, there is an opposite and equal reaction. So the force that has to balance this, that has to balance the weight of the body, is called the normal reaction. So the force here that will balance is called the normal reaction. We call this I. Some textbooks will use N. Alright? Normal reaction, that's I or N. Okay? Now, so we have this. So we just said that W is called the weight of the body, while I, we said, is the normal reaction. Of course, weight is measured in Newton, normal reaction also in Newton. Both of them are in Newton. In some cases, some texts will call normal reaction N. So now you want to call normal reaction as N or I, is the same thing, okay? Alright, so that's number one. So for this body now, it is not moving. So here's the thing, scene 1, if this body, let's say it moves towards the left, if the body moves this way here, of course, to oppose the motion of this body, I will have to move in the opposite direction. So hence, if this body is moving to the left, the frictional force will move to the right. So I have this. Alright, so this is scene A. Scene A says if a body is moving towards the left, to oppose the motion of this body, the frictional force has to act in the opposite direction according to Newton's third law, and hence frictional force goes to the right. That's scene 1. Scene 2. What if we reverse the case? What if the body moves to the right? Obviously, for frictional force to oppose the motion, it has to move in the opposite direction. So hence, if the body is moving towards the right, the frictional force will move towards the left. So I have this. So these are like two scenarios where frictional force works. So the idea is very simple. Frictional force will always act in the opposite direction of the motion of a body. That is the direction for frictional force. Having considered this, let's look at the types of frictional forces that we have. So next up, let's look at the types of frictional forces. There are two types of frictional forces. The first one is called the static, also known as the limiting frictional force. The second one is called the kinematic, also known as the dynamic frictional force. Alright, so let's consider these two frictional forces and what they mean. Alright, so we said there are two types of frictional force: the static, also called limiting frictional force, and also the kinematic, also known as dynamic frictional force. What is static or limiting frictional force? Static or limiting frictional force is the maximum force that must be overcome before a body can just start to move over another body. That's enough. That is static or limiting frictional force. For example, if I have a body, as I drew earlier, if I have a body on a rough surface as this, the maximum force that must be overcome before this body can just start to move over this surface is known as the static frictional force. This is case 1. Next up, let's look at kinematic or dynamic frictional force. By definition, kinematic or dynamic frictional force is simply the force that must be overcome, or the force that must be overcome before a body moves with a uniform speed over another body. That is kinematic or dynamic frictional force. So the force responsible for placing a body in uniform speed over another body is what we call kinetic or dynamic frictional force. Alright, so having considered this, let's look at a concept in frictional force. Now we said when a body is placed on a rough surface like this, we said the forces that act here include number 1, the weight coming downward, number 2, the normal reaction going upwards, number 3, depending on the direction of the motion of the body. If the body is moving this way, if this is the direction of motion, then we said frictional force FF. So if this is the motion of the body, then the frictional force will act here. Let's call this F. Please, F here is frictional force. Let's indicate that F is equal to frictional force. Frictional force. So we have this, of course, also in Newton. Of course, force in Newton. So we have frictional force in Newton. Now, having considered this, let's look at something. From experiments, it has been seen that the value of the frictional force is roughly proportional to the normal reaction. So, frictional force, you can say roughly it is proportional to the normal reaction. So we have this. And from the idea of mathematics, we said whenever you have a proportionality sign, we take off that sign and introduce a constant. Of course, equal to and a constant. So that means the frictional force changes to equal to. My constant in this case becomes mu, then r. So we have mu here. If I make mu subject to the formula, I'll have to divide here by r, divide here by r. This cancels this. So this mu is equal to f all over r. Let's include units. We said force is measured in Newton, normal reaction also in Newton. So this is a case of Newton cancelling out. So therefore, this mu has no SI unit. So I have this. Anyway, this is called mu, pronounced mu. This is the constant of proportionality known as coefficient of friction. Known as coefficient of friction. Now, mu exists for both static and kinematic. Alright? For static, we have mu s. This is called the coefficient of static friction, and we have mu k. This is called the coefficient of kinematic friction. So that's it. So we have this concept. Alright, so we use this concept in solving some examples. But before then, it is important that you know that the value of the coefficient of static friction is greater than the value of the coefficient of kinematic friction. This is because more force is needed to make, we said for static friction that it is the maximum force that must be overcome before a body can move or can start moving over another body. And we said for kinematic friction that we said it is the force that must be overcome for a body to move with uniform speed over another body. Now, it's quite obvious that more force is required for a body to start moving than is required to place a body in uniform speed. So I need more force, right, to push a body that is at rest to start moving than I need to make a moving body to move with uniform speed. So for this reason, since I need more force to move a body from rest than I need to keep the body in uniform speed, we can now say that the coefficient of static friction is greater than the coefficient of kinematic friction. Alright, so with this, let's solve some examples and some past questions. Okay, so let's take this sample problem. It says, what is the coefficient of friction between a wood of mass 1.6 kilogram and a horizontal surface if the limiting frictional force is 8 Newton? Alright, let's get this done. So solution, I will try to list out my given parameters so I can see what I have. Number one is said, what is the coefficient of friction between a wood of mass 1.6 kilogram? The first is there, I'm giving number one. The first I'm giving is the mass of wood, mass M is equal to 1.6 kilograms. So we have this. Next one it says, and a horizontal surface, if the limiting frictional force is 8 newtons. Number two, we have frictional force of the house. Limiting frictional force as 8 newtons. They said, what is the coefficient of friction? So number three, mu, coefficient of friction is unknown. So let's solve this. Now to get this done, we'll have to recall our formula. Recall that we said mu is equal to F all over R. Frictional force all over normal reaction. I already have the value for frictional force F, which we said is 8 Newton. My next task will be to calculate the value of normal reaction. From my diagram I drew earlier, we said this, that for this particular scenario, I have weight acting upward and I have normal reaction. I have weight acting downwards and I have normal reaction acting upwards. And we said that the normal reaction is equal to the weight of the body. But also we know that weight is equal to the product of the mass of the body and acceleration due to gravity. So hence, we can say that normal reaction is equal to mass times gravity. If I include this, the mass of the body is given by 1.6 times acceleration due to gravity is usually 10 meters per second square. Well, except you're given 9.8. For this one, we're taking this as 10 meters per second square. If we multiply these two, we'll have that the value of the normal reaction is equal to 1.6 times 10. That's equal to 16. Of course, 16 in Newton. We said normal reaction is measured in Newton. So therefore, the coefficient of friction is equal to F all over I. That's equal to F. Frictional force, we said, is 8 Newton all over I. Normal reaction, we said, is 16 Newton. Alright, so if I work on this, Newton cancels Newton. 8 here, 1, 8 here, 2. That's equal to 1 over 2. In decimal, that gives you 0.5. So the coefficient of friction is 0.5. Remember we said it has no SI unit. So my answer to this question is 0.5. So this is how you solve this question. Let's look at yet another question on friction. Now it says a motorcycle of mass 100 kilogram moves around in a circle of radius 10 meters with velocity of 5 meters per second. Find the coefficient of friction between the road and the tires. Take gravity G as 10 meters per second square. Alright, so let's get this done. Solution. My task, as usual, first of all, list out given parameters. What am I giving there? They said a motorcycle of mass 10 kilogram number 1. I'm giving the mass M as 10 kilogram. They say it moves around in a circle of radius 10 meters. Number 2, I'm giving radius R as 10 meters. Next up, with velocity of 5 meters per second. Number 3, I'm giving velocity V as equal to 5 meters per second. Alright, we said find the coefficient of friction. Number 4, the coefficient of friction mu is equal to unknown. G said is 10 meters per second square. So we have this. Alright, so we have to find coefficient of friction there. But here is a peculiar case. It's peculiar because this body is not just moving, but moving in a circular path. And when a body is moving in a circular path, we said the particular force responsible for keeping a body moving in a circular path is called the centripetal force. And centripetal force F is given by mv squared all over I. Alright, so the kind of frictional force that will act here will be perhaps a centripetal frictional force, which is given by mv squared over I. This is the formula for calculating the centripetal force acting on the body or causing the body to keep revolving in a circular path. If I impute values here, we have that the force F is equal to M, that's equal to M, the mass is 10 times V squared. V is 5, that becomes 5 squared all over R. R here is 10, so I have 10, so I have this. If I work on this is equal to, obviously from here, an easy part. 10 can cancel 10. So F is equal to 5 squared. That's equal to 25 Newton. So the frictional force in this case becomes 25 Newton. Now I'm repeating myself. I said the reason why I am calculating force using this particular equation is because it's a centripetal force. It's moving a circular path. And for centripetal force, the force is equal to mass velocity squared all over radius of path. That's it. Next up, let me get we have to find coefficient of friction. We know that the coefficient of friction, mu, is equal to F all over R. So far, so good, we've gotten the value for F. Let's now get for R, normal reaction. But we said normal reaction R is equal to weight, which is equal to mass times gravity. So hence, normal reaction R is equal to mass. Mass is the same mass. Of course, mass is constant, it doesn't change. That becomes 10 times gravity. We have to use acceleration with gravity as 10. So that's 10 times 10. That's equal to 100 Newton. I have this as 100 Newton. So therefore, we say mu is equal to F all over R. That's equal to F. Frictional force F is 25, that's 25, all over R. Normal reaction is 100. If I work this out here, 25 cancels itself, 1, 25 here I have 4. The frictional force, the normal reaction, mu, is equal to 1 all over 4, which in decimal gives you 0.25. Of course, there is no SI unit, so mu is equal to 0.25, and that's the answer. Alright, so this is how you solve this particular question. Let's consider one last example under friction. The example says, the diagram shows a wooden block just about to slide down an inclined plane, whose inclination to the horizontal is alpha. The coefficient of the frictional force between the block and the plane is, so you have your options there. Alright, let's get this done. So we have this as a case. We ask to find the coefficient of friction in this case. What do we do? Now, first things first, this is an inclined plane. We've already dealt with inclined planes in a previous video. I'll leave a link to the video on inclined planes in the description of this video. Alright, so at this point here, let's deal with this. So first things first, here's what we know. We said when a body is placed on a surface, as in this case, that what acts here is called the weight. What acts here is called normal reaction. For here, they call it a block. So perhaps, let's say when a block is placed, weight acts this way, reaction acts this way. We said if this is the motion of the body, here is the frictional force. So we established this fact in our previous conversation. So let's use this idea here. What if this is no longer a rough surface like this? What if it is now an inclined plane? Now, here's what we know. Number one, weight acts this way. Now, if I look at this correctly, normal reaction acts upward. So upward here should be normal reaction, that's R. This is normal reaction, R. That's number one. Next up, you would assume that normal reaction and weight are in a straight line. That means from here, I should have taken a straight line this way. I should have my weight acting this way. That's weight acting this way. W. This is what we should have. This is what we should expect from this diagram. But in reality, this is not so. The idea is this: weight always acts vertically downwards. So in this case here, your weight cannot act this way. This idea of weight acting this way is not practical. In a practical sense, the weight will now act this way. It must be vertically downward, W. to have this W. So the weight must always act vertically downward. Irrespective of how you place the body, the weight will always act vertically downward. So we have this. So this becomes weight. But then this should be my hypothetical weight. This one here, what I'm saying, opposite the normal reaction. If that is so, we'll have to do a little bit of analysis. And by analysis, we have this. If a body is inclined on an angle alpha to an inclined plane, the angle between the hypothetical weight, that's this one here, and the real weight, this angle here, will be the same thing as this angle here. So here, it still becomes alpha. So we have this. So hence, we can see that the weight is inclined at an angle alpha to the vertical. That's the idea. The weight. So if I have this becomes my horizontal line. This becomes my vertical line. This way. So I'll just call this a V. This V. V means vertical line. H is horizontal. So it was just this, but it has this. So this is my horizontal. This is my vertical. It was just slanted like this, and I have this. This is still the horizontal, that's this. And this is still the vertical, that's this. Alright, so in this case, here's what to note. When a force or when a vector is inclined at an angle theta, or in this case alpha, to the vertical, the horizontal component of this vector, that's the one that acts here, is given by this W. This one here is this sine theta. That is this part here. Alright. While the vertical component is given by W is equal to this is equal to W cos theta. Why we are having W sine theta and cos theta is because we are resolving this both horizontally and vertically. So this one has already been explained in another video. So just note that if a body is inclined at an angle, we are using alpha here. So hence, let's use alpha instead. Cos alpha, cos of the angle. And here, cos alpha, cos of the angle. So if a body or if a force or a weight or any other vector is inclined at an angle alpha to the vertical, the horizontal component becomes this, that vector, in this case weight, sine of the angle, and the vertical component becomes that vector, cos of alpha. Alright, having established this, you can see that R is equal to this one here. So R is equal to, from here, we can see that R is equal to, this one is equal to this one here, W cos alpha. So we have this. While this one here, for this, if I compare this to this one here, of course this one will slide there. This becomes the motion to slide there. Frictional force will act this way, trying to oppose this block from sliding down. And the frictional force F is equal to the motion, that's W sine, that's W sine alpha. So we have these two identities. So therefore, the coefficient of friction, this mu, is equal to F all over R, and that's equal to F is W sine alpha all over R is W cos alpha. From here, W cancels W. So coefficient of friction is equal to sine of alpha all over cos of alpha. And if you're familiar with tree, that's trigonometric identity, we said sine alpha over cos alpha gives you tan alpha. Alright, so this becomes your answer. Hence, the answer to that question is tan alpha. So this is how you solve this particular question. So we'll end by looking at some of the advantages, disadvantages, and some ways in which we can reduce friction. Let's start with the advantages. Some of the advantages of friction is that friction helps us to walk, to run, to jump. So I can actually stand here, or I can move around here because there's friction between my toe and the ground. Friction also helps us in grabbing things. The reason why I can hold this piece of chalk is because a frictional force exists between the chalk and my hand. If the chalk is too slippery, what you observe is that it will fall off from my hand and I can't hold it. In fact, this explains the reason why you cannot hold slippery objects. So why is that? Whenever you hold a slippery object, it just falls from your hand. Or perhaps if you step on a slippery ground, or perhaps a wet tile, for example, a tile that is wet, you slip and fall. Why? Because there's little or less friction there. Alright? So the advantage is that number one, friction helps us to run, to jump, to walk around. Number two, friction helps us in grabbing things like this. Okay. Number three is that friction also helps in belt drives. All right. In case of pulleys, where you have belts on pulleys, the reason why those belts can actually connect to those pulleys is because there's friction existing between them. So these are some of like the examples or the advantages of friction. So aside these advantages, what disadvantage or disadvantages does friction possess? Number one, friction causes wearing and tearing. And this is why you have to change your car tire regularly. Alright? It becomes slimmer in quotes as you use them. Why? Because the surfaces of objects wear off due to friction. Okay? When they rub against each other, they wear off. That's number one. So the first disadvantage is that friction causes wearing and tearing. That's number one. Number two, friction causes loss in the efficiency of machines. We treated efficiency of machines in a previous class. There we said that the efficiency of a machine cannot be 100%. Why is this? Because some work is done to overcome friction. So since some work or some useful work is being done to overcome friction, the efficiency of the machine cannot be 100%. So that becomes a disadvantage of friction. It reduces the efficiency of machines because some work has to be done to overcome that friction. The third disadvantage of friction is that it causes the heating of engine parts. And this is why if you ride a car for some time, by the time you park and you touch the car, the engine part especially, it's very hot. Why is it hot? Because of what useful work has been done in terms of, or useful work has been done to overcome friction. Alright, number three is that friction causes the heating of engine parts. So these are like some advantages and disadvantages of friction. Finally, how can we overcome friction? We can overcome friction by number one, lubrication. Alright? Number one is lubrication. What is lubrication? Lubrication is simply a process of adding what we call lubricants. Alright? Lubricants. Lubricants such as engine oil, such as palm oil, and some other things there to reduce the friction in machines. And this is why you add engine oil to your generator set, to your motor set, and etc. Alright, so number one is through lubrication or the addition of lubricants. The second way of using friction is by using what is called a roller bearing or a ball bearing. And a third way of reducing friction is by streamlining engines or machine parts. When you streamline machine parts, it becomes easier for them to overcome air resistance and thereby overcome friction. So these are three ways in which you can overcome friction. Number one, lubrication. Number two, use of ball bearing or roller bearing. And number three, by streamlining engines. So that's for friction.